Let's do one more example. Say that the building specifications in a certain city require that the sewer pipe used in residential areas have a mean breaking strength of more than 2,500 pounds per lineal foot. A manufacturer who would like to supply the city with sewer pipe has submitted a bid and provided breaking strength observations for 37 randomly selected sections of the pipe. The sample mean of these 37 observations is 2,571.43 pounds per lineal foot, and the standard deviation is 115.1 pounds per lineal foot. Let's use the p-value approach. Okay, so we want the breaking strength here to be greater than 2,500 pounds per lineal foot. Greater than. Greater than does not imply equality, so equality we know is in the null, so the greater than statement must be in the alternative. Okay, so mu here must be less than or equal to 2,500 pounds per lineal foot. The alternative must be greater than 2,500. Okay, we collected a sample of size 37, found that y bar, the mean of that sample, is 2,571.43 pounds per lineal foot, and S, the sample standard deviation, 115.1 pounds per lineal foot. Okay, so we know all this. We know that we have a hypothesis for means. We know that we have standard deviation in place of sigma. So we're going to have to use a t distribution for our test statistic. So our test statistic, again, is y bar minus mu naught divided by S over root n. Okay, y bar 2,571.43 minus mu naught, the hypothesized value, 2,500, over S, 115.1 over root n, root 37. Okay? And if we work that out, it's just arithmetic, we should get 3.22. Okay? So now we're going to use the p-value approach. The p-value approach. And we're going to find the area associated with the test statistic in the upper tail. Okay? Degrees of freedom here is 36. T, 36. N minus 1, 37 minus 1 is 36. Okay, here's 0. Here is our test statistic, 3.22. And we know if a greater than sign is in the alternative hypothesis, then the p-value it lies entirely above the test statistic. So here's the p-value right here. Okay, so we got to find the area in the tail for degrees of freedom 36 associated with this value 3.22. Okay, but we don't have in our t table degrees of freedom 36. Past a certain number, it only goes by tens, and then past 120, it jumps to an infinite number of degrees of freedom, which is a z distribution. So we don't have 36 exactly. If you want to be conservative, and let's say we do, let's say we want to be conservative about testing this set of hypotheses, then we want to round down to degrees of freedom equals 30. Okay? So if we round down to degrees of freedom equals 30, what do we see? So we go to the line associated, or the row associated with degrees of freedom 30, and we see this. We see 0.005 in the upper tail. Okay, so we go to that column, 0.005, and that is a value that's associated with the value on the t-axis of 2.750. Okay, and I'm going to try to do this such that it looks good. Here's t of degrees of freedom 30. Okay, and if we go over and find 0.001 in the upper tail, that's associated with a value on the axis of 3.385. Okay, 3.385. And our value, 3.22, the one where we want the area of, is in between these two. It's in between. Okay? Here, of course, these aren't lined up beautifully, like I would hope they would be, but this is 3.22 on this axis, right? So we know this area, we know this area, and we know that this area is somewhere in between, but we're not exactly sure what. Okay? So at a minimum, what we can do with the t-distribution table is just bound this area, this p-value right here, the area in the tail above the test statistic, between 0.001 and 0.005. Okay, so at a minimum, we can say this. The p-value is greater than 0.001 and it's less than 0.005. Okay, that's a small p-value. Okay, that would be, with most anyone making a judgment here, we would be rejecting the null and concluding that the pressure that can be exerted on these pipes is greater than 2,500 pounds per lineal foot. Okay, so we're going to reject the null with such a small p-value. I mean, if you compared this to alpha of 0.1, 0.05, 0.001, this p-value is still smaller than any value of alpha that we might choose. Okay? But let's say we have Excel at our disposal and we want to counter this problem with degrees of freedom. We can use Excel. Okay? We can use the t-dist function again. Okay, remember the t-dist function, if you start typing in t-dist into Excel, okay, it will tell you what it wants you to enter. Okay, and what it wants you to enter is the value on the axis. Okay, in that case, this is our test statistic. Then we read in the degrees of freedom, and we tell Excel whether it's a 1 or a 2-tailed test. And so we type in 1, okay, because this is a 1-tailed test. All of our area is in one tail in the upper tail that we're interested in. Okay, so how we're going to implement this, the t-dist function, is by typing in the test statistic, 3.22, degrees of freedom, 36, okay, 37 minus 1, we can put that in directly. We don't have to round down. And 1 in the one tail. It's an upper tail test. And if we do that, we get the value 0.0014. Okay? 0.0014 lies between these two values. Okay? So we could estimate it this way. We're still going to reject the null. Okay? Or we could find it more explicitly using Excel. And again, it's still a small value. We would still reject the null here.